Let's take a look at timing adjustment, and we will then show when we have a zero coupon bond, the timing adjustment and the convective adjustment is actually the same. For timing adjustment, we're having a situation where we have a contract that pays at a time t, big T star, of the value of some variable observed at t, and t star is greater than t, so at a later time. So we observe something first, but we don't pay that observed value right away. We pay that at a period later. Now, an example of that will be that, say you observed the TSX index value at the end of year 3. So, this contract may pay you that observed value, but instead of paying you at year 3, it's paying you at the end of year 4. So like a year later or something. And in this case, in our calculation, we would need to go through a timing adjustment for us to calculate our value. Now, why is that the case? Now, normally, if we just set up from a equivalent martingale approach, you will have using zero coupon bond as numeraire. So you basically would do that. Okay, I have a zero coupon bond that matures at time T star. If the payment is paid at T star, you will have, you would have been chosen a zero coupon bond that matures at time T star as a numeraire. So if you do that, the current price of the derivative asset divided by that zero coupon bond is equal to the expected value of the payment at T star divided by the zero coupon bond at T star, which is 1. So in that case, you would you have an expectation of T star here, and you would have a V at T star. Okay. Now here in our problem here, we don't have this one V is a VT star. We have VT. So it's not the realized value at T star. The payment is according to the realized value at T, which is a period earlier. But the expectation here is based on a zero coupon bond that matures at T star rather than T. So we have a mismatch here. So had this been a VT star, then we won't really have any problem. But in the market, we have VT star, expected value of VT star based on this zero coupon bond. But what we need is this thing here, which we do not observe. Instead, in the market, we typically observe either, expected VT, but the expectation is taken as with the zero coupon bond that matures at T. Okay, we have that, or we have the value at the payoff at T star, and the expectation of that is taken with a zero coupon bond matures at T star. So we have those two, but we don't have this, which is something we need. So we have to generate, we have to obtain this through an adjustment. So the way we do that is we will change numeraire to obtain this expected VT, the expectation using a zero coupon bond matures at T star, from this expected VT, but with a different zero coupon bond as a numeraire. So basically, if we look at the way we have done the adjustment on the drift to handle a change of numeraire, we will see that this value that we need is basically this value that we have, which we can observe in the market, multiplied by this factor here. This factor is just a change of the drift when we have a proportional drift. Now, because we're looking at a log normal process, so the adjustment here is, where the change of the drift is just not a direct multiple of this thing here. It's e to the power of this thing, because we're looking at a log normal process. So you can review some of the change of numeraire that we have discussed in lecture 3. So how we change from a numeraire, we use G as a numeraire asset to another process that we use H as a numeraire asset. So this becomes this alpha F is the change of drift. Okay. So now to change from this expectation to this expectation, we first define a ratio. So you have seen this earlier, right? So the ratio is, like this here. So we define a ratio between two different numeraires. So this is a numeraire H, and this is numeraire G. So you are changing from G to H. Basically what we do is to find this, which is G with T to T star. So we're changing from this to here. This will be numeraire G, this will be numeraire H. Now to do that, we can just easily plug in this drift term as rho between these two, W and V, two different assets, and we multiply sigma W and sigma V. So just here, it's consistent to this thing here. So this F becomes V, and W is still called W. And rho is the correlation coefficient between W and F here, which is correlation coefficient between W and V. So, so we define W this way. Is there a contract in the market that is really W here? Okay. In general, we don't really observe a contract that is exactly W. So what do we do? Well, although we don't have a W observed, but we do have a relation between W and the forward interest rate. Okay, and the reason for that is there is a relation like this here. So if R is the per annum forward interest rate between T and T star, okay, so it's a forward interest rate annualized, then we have seen earlier that this condition must be true. So if this condition is true, we can then find out this process from here. Okay, just to to record the memory. So we have seen in lecture 3 about forward rates. And we have derived that forward rate is of this particular form that's consistent to here. So this will be a W. Now there's a little bit of a difference in expression here. So we have an M here, and in the earlier ones we don't have that. So why is there a difference in the expression? Well, in the first expression here, this T star minus T is a multiple of years, and the interest is compound M times a year. So this is like 5 years, and this is like 4 times a year, okay? So in the second expression, T star minus T is a fraction of a year. So, I mean, if we are looking at 3 months, then it's really this. But here, we're looking at this expressed in terms of years rather than in terms of a fraction of a year. Okay, just a different way of re-expressing the time scale. Well, given the relationship, then we can then express this sigma W with something called R and sigma R through ethos lemma. So if we look at dW, it should be something drift and plus a volatility term here, and dr is a drift times volatility, but they're linked through a function. Then we can use ethos lemma. So by ethos lemma, dw is then the derivative between dw, the first partial derivative of dw. So then it's dw dr, and then times sigma r will be this term. Because we can ignore, when we done ethos lemma, we don't really have to calculate drift term, because what we're interested is really the volatility term here. So you've done that, the volatility term expressed in terms of R and sigma R is this. And this must be the volatility term for dW, which is this. So sigma W times W is equal to the derivative, the partial derivative here times sigma R times R. So now we know since we know the functional form here, this W is really this, which is really can be expressed here. Then we can explicitly derive the partial derivative, which will give us this. Now, we have the partial derivative, then this thing times sigma RR equal to that will imply that sigma W is equal to this. With this sigma W calculated this way, so you have this thing basically divided by that, you have this. Now, you just substitute it in. So here we have rho between W and V times sigma W sigma V. You put in sigma W, this here. Sigma V is sigma V. Now, why do we then turn this thing, the correlation between W and V, into a correlation between R and V with a minus sign here. Now, this correlation between W and V and the correlation coefficient between R and V, people typically would think, well, W and R are negatively correlated. So instead of just the correlation is 1, but it's negative correlated, when you convert from this to that. When I say correlation is equal to 1, doesn't really mean this row is 1. What I meant is this row value and this row value are the same, but there should be a minus sign because this correlation and this correlation are negatively related. Now we don't see that negative sign here because this negative sign is actually from here, from this sigma W here. So sigma W is negative of this thing. So we didn't use that. We just directly use this number. Why? It's because we actually have handled this negative part when we calculate this partial derivative. Because change of W, dW, dr is a negative value. So we already handled that negative value, that sign, through this partial derivative. So here we don't have to handle that sign again. That'll be double counting. So we just take this value, which is exactly this value here. Okay, ignoring the negative correlation because negative correlation has been accounted for here. Now, we calculate this alpha V here in this expression. So we can just plug in that and said, okay, if we need to change numeraire, that so we have to adjust, to get this particular thing, where we take expectation of VT, but with the numeraire that is a zero coupon bond mature at T star, we can use this expectation, but adjust it by this drift change, which is e to the power of this thing we derived. So basically e to the power a alpha v. Okay, let's take a look at an example here. So to demonstrate the timing adjustment, let's see, say we have a contract that will provide a payoff in 6 years equal to the value of a stock index that you observe in year 5. And so the market exists a forward contract that is based on the index value. So the forward contract, a 5-year forward contract basically, has a price of 1,200. So which is the expected value or the forward value of this index. We know the volatility of the index forward, which is this forward, is 20%. And you can obtain that through some options on this forward. Okay, so the forward contract that, on a year 5, if whatever the stock index value is, that's how much the contract's gonna pay you. If the index value in a year 5 is 1,000, the contracts pay you $1,000. If it's 2,000, it'll pay you $2,000. And that particular contract right now has a value of $1,200. And the forward interest rate, this from year 5 to year 6 is a 1 year for interest, 1 year interest rate, 5 year out, has a volatility up to 18%. Okay, and you also have to obtain this from an option somewhere because it's talking about volatility of a full interest rate. And in order to back out volatility, you have to have options. So however, you are able to obtain them because you have typically option existed for those contracts. Then you can back it out the volatilities that way. Now you can also measure the correlation between interest rate and stock index as typically negative correlated, so minus 0.4. Suppose you have a discount curve. So this basically risk-free zero curve. It tells you the term structure of discounting factors. Okay, so here for simplicity, it just says for 8%, but it could be a term structure, so that will have a different rate with a different maturity term. So what is the value of V? Well, you know that since the payoff is observed in year 5 but paid in year 6, you will have to go through a timing adjustment. This is in contrast of rates, where in rates, typically you observe in one time period but paid out in the next time period. But that is okay because your rate is not a price. So if you have a 1 year rate, if the contract is instead of not based on the price, but based on the rate, which is paid out, observed in year 5, but paid out year 6 for based on a 1 year rate, then you don't need this adjustment, okay? You only need this adjustment, this timing adjustment, if it's a price that you observed at year 5, but that value is paid to you at year 6. So for the example that we've had, just put in the numbers, the correlation is 0.054, 20% volatility for V. For the rate, the volatility is 18%. 8% is the initial, is the discounting, and big T is 5, T star is 6, M is 1. This is 1 period, 1 year. So if you look at it, your expected value of VT using a numeric asset of a zero coupon bond that matures at big T is 1200. Okay, so it's important to recognize what this 1200 is. This 1200 is this particular expectation, but you need a different expectation. So your adjustment factor is put in the expression we derived earlier. Based on those information here, it gives you 1.00535. The discount over 6 years is 8% a year over 6 years. It's 0.6302. So your current value is basically the discounted value, which is this, times this whole thing is the expected value of VT, where you would have a T star here. Okay, so E T star VT is this whole thing, which is 1200 times 1.00535. So put everything together, the value of the contract is $760.25.